So look, so what we were just talking about is fine for calculus class where you got all those fancy little Greek symbols. And you probably by now wish you were paying a little more attention to those Greek symbols. But the question is, how do we do these things in a computer where we don't get to do continuous math? So to do that, we have to talk about discrete gradients. So in continuous math land, the partial of f with respect to x is just this limit, right? So we move a little bit in the x direction, epsilon, subtract off the original one and divide by epsilon. And when we let that limit go to 0, that becomes our derivative. But in discrete world, we can't move arbitrarily close. We have to take what are called finite differences. So what we're going to do is we're going to talk about approximating our partial by some finite difference. So the simplest finite difference is this one, right? I take one step in the x direction and I see what the value of the function is, and I subtract off the original and I divide. How big was the step? Just 1. So that just becomes this value. So we say it's approximately f of x plus 1 minus f of x, okay? And that's called the right derivative. You get it? Because it takes step 1 to the right. Oh, wait. 1 to the right. Yeah, right, left, for those of you who aren't looking at this thing in a mirror. Okay? In order to talk about the right way to think about these derivatives, let's take a look at our finite differences a little bit more. So here we have a picture of the striped duck that David puts in his book very often, David Forsyth. And you can see here we have this, it's a zebra, okay? So we have this picture of the zebra which has all these stripes on it. And over here we have one of those finite difference images. First question, is this the finite difference in x or in y? Well, let's take a look. Here I have these nice kind of almost vertical stripes, and as I go across, you can see that I get a bright value and a dark value and a bright value and a dark value. So in other words, as I'm seeing changes going horizontally in x, I'm getting different values of whatever this finite difference is. But across here, I have hardly any changes in x and only changes in y, and you'll notice this is not a very strong signal there. Okay, so this is going to be a finite difference in x. One of the things that might be bugging you about this is on the right-hand side here, I'm showing you an image that has positive numbers and negative numbers in it. So here's the deal. Normally when we display an image, we make 0 black and some other number white. Or we say some minimum value is black and some maximum value is white. Oh, I didn't say it has to be 0, it has to be some minimum. So I could make like minus 128 be black and plus 127 be white, or minus 20, and I could make 0 be gray. So what you're seeing here on the right is what's referred to as a gradient image, where gray is 0, white means positive, black means negative. This is sort of mess you up in doing some of the problem sets, etc. But remember that the display of an image is just for convenience for me and you when it's a mathematical function like this.